All right, good evening. So this is the second video related to homework number 9. What we're going to work on is another transient case. The first transient case we did was the lump capacitance method, where we had a really small object that was, say, like put in a bath, and we could treat the whole thing as having a uniform temperature. What we're going to do now is take a look at cases where the temperature of an object can't be considered uniform. And the easiest case, great one to get started on this idea of transient, is to take a look at a plane wall. So we're going to get a plane wall where we're going to consider the x-axis to be going into the wall, 0 being exterior surface of the wall, and we're going to see if we can come up with a function that gives a temperature at any position in the wall at any time. So a function of two variables, pretty challenging. The wall doesn't need to be horizontal. There's a problem on homework number 9 where we're actually taking a look at the temperature in the surface. So that would be the surface, the Earth. So the Earth's surface could be considered a plane wall, and 0 could be the surface of the Earth, and x could be going down into the Earth. All right. Trying to put some numbers on it, take a look at a particular example. We'll take a look at, say, for example, the heat shield. Where we'd be interested in the temperature within that heat shield as a function of time. So the particular example I'm going to take a look at is a heat shield maybe for some sort of rocket or some sort of other device re-entering into the Earth, going through the Earth's atmosphere. So we're going to take a look where we have some sort of thick shield right here, and we'll say like it's initially all at 20 degrees C. So everywhere inside there, it's a pretty moderate temperature. So 20, 20, 20, all the way across. So that's the initial temperatures. Okay, and then we'll make this this side over here, okay, the side over here to be the inside, and then over here is going to be the exterior, where it's going to warm up because of friction rubbing against the Earth's atmosphere. We're going to have it warm up to a pretty high temperature, which is not atypical. You've probably seen this, and sometimes those surfaces get incredibly hot. So we're going to have it warm up to 700 degrees C, and so then we're going to essentially wonder, well, how long does it take that temperature to penetrate into the wall? And is our wall thick enough? So let's say if we'd say the re-entry takes 8 minutes, well, is it going to be? It's definitely going to warm up in this area over here. That would make total sense. I mean, if it's 700 degrees C, and this is some material, the heat's definitely going to penetrate in here. But would it penetrate all the way over here? We hopefully not, because we would like inside whatever's penetrating the atmosphere. We'd like this interior area to remain cool, not super hot. And so we're hoping it doesn't penetrate. So how would you go about doing that? How would you go about coming up with a function that would give us the temperature at any position in this wall? So we're going to call this direction the x-axis. Sorry about my writing upside down here. And at any position at any time. All right, so give me a second to erase the board and we'll get going on it. What we're going to do is combine two important ideas this semester for that wall. One is thinking about the heat transfer in that wall. What kind of heat transfer would be occurring in that wall? So if I drew this wall here, okay, and if I went to any sort of interior point within that wall at some position x, well, would the type of heat transfer going on there be convection, irradiation, absorption, emission, or conduction? And clearly it's conduction. We're inside a solid. So just a reminder, Fourier's law says that the conduction at that point is going to be equal to negative k times the rate the temperature is changing in the x direction. So that's a basic idea on conduction in the wall. That's what's occurring. Okay, and then the other thing is that also it's going to be true at any point in that wall is the first law. Okay. Plus one more term, E dot gen. Okay. If I go to any point in that wall or any little area within that wall, okay, if there's any storage occurring, it would be the difference between the rate which energy is flowing in minus the rate that energy is flowing out plus the rate of energy generation within there. Okay, and it turns out that what we're going to do is we're going to start with this equation right here and try to write an equation that's true for this sort of scenario where we have a plane wall where heat's conducting through. and throw in Fourier's law, and with a little bit of algebra, we'll get an equation that will allow us to finally end up with our function t at xt. So that's the goal. We'll start right here. So give me a second. The way this is normally done is we just take a small section of the wall. So I'm going to draw the wall a little bit neatly. So I'm having a little trouble writing upside down. So I'm going to draw the wall. Okay. All right. And we're going to try to write an equation that's true at any x. Okay. So what we're going to do is just take a slice of that wall, and its left side is going to be at x, and its right side is going to be x at dx. And that's essentially going to be our control volume for which we're going to write the first law. So let me get that up there. Get a picture of that. Thanks for your patience on this. Okay, so what does this picture represent? This side right over here is a slice of the wall. That's the slice of the wall, okay? And we know that heat's going in and heat's going out. This side is at x. This side over here is going to be at x plus dx, okay? And what's got conservation of energy is always got to be true. So we're going to write that equation for this section of the wall and see if it can allow us to get to the point where we can come up with that temperature function that we're after. Okay, so give me just a second. I'm just going to go ahead and start in on it. So the first thing that we can do is, let me get the first law up there. Okay, and I'm going to be less slick about it than I could be. Anytime we've written the first law for anything, we've tried to say, hey, would any terms be zero? So let's go through that really quickly. Storage, would storage be zero? Well, storage is zero if it's steady state, and this is not. This is transient. This wall's temperatures are changing with time and at various positions. So storage is not going to be zero. Okay, how about generation? So imagine a heat shield for a capsule that's re-entering the Earth's atmosphere. Would you want something inside it that generates heat? And the answer is obviously no. You wouldn't want that because you're trying to keep it cool. So that would normally be zero. I'm going to make it zero a little bit later on. So let's go ahead and go through this. For storage, it would be the volume of this times the density and its specific heat, and then both multiplied by the rate of change of temperature with respect to time. So that would be rho CV dt dt. So that would be the rate of storage. And I did a partial derivative because temperature is changing with both time and position. Okay, how does heat getting in? How is heat getting into this? Well, it's conduction, so it would be Fourier's law. So for the first one, I would do negative k. We'll get that up there in just a second. dt dx at x times the area. Okay, good. So basically that first term gives the rate at which heat is getting in. I should do something with the volume to make it a little bit easier. The volume of this slice right here is its cross-sectional area times the width of this slice, which is dx. So I should have written the volume as area times dx. Give me a second, I'm going to do that. Okay, so far what we have is we got storage equals in, okay, and then we might have to do minus out. So I'll do that down below. That's also going to be Fourier's law. Okay, so Fourier's law, k times dt dx, but now we're on this other side over here, this right side, and so our position is at x plus dx. Multiplied by area, okay, because we're trying to get total energy in. And then the generation term. Okay, so generation is a lot of times written by taking what's termed the volumetric generation, Q dot, and multiplying it by the volume. So plus Q dot A dx. All right, so let's take a look at that for just a second. That is our general equation. We got one. Let's see, 1, 2, 3, 4 terms. All right, and we're supposed to use that to come up with an equation for temperature at any position at any time. Well, obviously the first thing to do is to see if there's anything we can do to simplify, and a couple things become pretty obvious. First of all, there is an area, okay, in each term that can be canceled out, right, and get rid of all those areas, okay. And so what I'm going to do is write another line where I got rid of all the areas. Try to put it all in one line so it's a little easier to comprehend. Okay, all right, and I just changed the order of those ins and outs. So this is actually the out term and this is the in term, all right? And then the next thing that's done actually is you can divide everything by dx's and you get a much simpler equation. So I'm going to divide all 4 terms by dx, and I'm going to do one other step. If I take a look at this term right here, I've got a derivative with respect to x, another derivative with respect to x, a difference, and I divide by dx. Turns out that's the second derivative. Turns out it's going to be the second derivative. So get that up there. Okay, so now it ought to go pretty quick. So there is our summary equation. That is sometimes called the one-dimensional heat diffusion equation. If you have some sort of solid material that heat's diffusing through, this is your governing equation. All right, so I wanted to get that up there. That's one of the basic equations in ME 126. I'm sorry, because of the time we have, we didn't really emphasize it. Something that you'll see again if you go on and do more heat transfer. In our particular case, we can simplify it more. First of all, we can get rid of this q dot gen, okay? And then secondly, what we can do is we can take this rho c and move it underneath the k, and that gives us that term for a solid, which is called k over rho c, which is the solid's thermal diffusivity. It's alpha, thermal diffusivity. So just a little bit of work on that. Okay, so for our case, if we have a solid and we've got no internal heat generation, there is our equation. We need to come up with a function where its derivative with respect to time is equal to a constant alpha times the second derivative of the function with respect to position. Piece of cake. Well, not really, actually. It's trying to come up with a function to do that. Let me just give a guess, all right? Give a guess. Okay. I am going to guess the following. Okay, so I'm just thinking about all the different functions out there and thinking, okay, maybe that will work. And one thing that was going through my mind is I want, when I do the second derivative of the function with respect to x, to get something back that's really similar to the original function, all right? So just thinking about it a little bit, if I took the derivative of this function with respect to time, I would get e to the t sine x, because the derivative of e to the t is e to the t. And if I did the double derivative of it with respect to x, the derivative of sine x is cosine x, the derivative of cosine x is negative sine x. And if you think about it some, this is really, really close to the right solution. But unfortunately, we're going to have a negative, so I can't plug this function in here and have it solve that and have it work for that equation. So that's not it. It is not that simple. All right. So what is it? I've always been pretty amazed by this. When I saw, the first time I had a professor go through and say, hey, there actually is an analytical equation which solves that differential equation, that partial differential equation. I was pretty surprised at it. And I'm not going to expect you to do the derivation. It's in the book. I believe it's in section 5.7. But I would like you to know a little bit of background on it. So what I'd like you to do is just start by thinking about what a graph looks like. All right? So I'm going to put a okay. So a common graph out there in statistics in particular, e to the negative x squared. What does that actually look like? All right. And if you think about it, if you put in 0 for x, e to the 0 is 1. Okay. And as you put in larger and larger numbers for x, it's going to get smaller and smaller and smaller. Okay. And it turns out, without a lot of plugging in numbers, pretty soon you start to see that's the bell-shaped curve. So sometimes this is called the error, something related to the error function that's called the bell-shaped curve. All right, what if you tried to integrate that? What if you tried to get the area under the curve? All right, you could spend a lot of time working on that, trying to get that exactly right and figure out what the area under that curve is. Okay, it turns out that there's no easy function that will give you the area under that curve, but nonetheless, if you go through and you integrate it, the area under that curve is the square root of pi over 2. So for those of you who like some math, that might be a pretty intriguing thing, that you're taking e to the x and you're getting the square root of pi over 2. Okay, I'm going to pause for just a second.